Hello, everybody. This time we are talking about lesson 14, solving systems of linear equations in two variables. Okay, the two variables part you should be happy to hear. Two variables right here. That means that these are not that hard. When you eventually in college algebra do three variable systems, this whole thing becomes much messier, but for our lesson today, just two variables, this will not be too bad. And we actually, believe it or not, already have a lot of experience doing what this lesson is about. We just didn't call it systems of equations before, but now we're going to formalize it and make sure we know exactly what's going on. So we're going to solve systems in three different ways: by graphing, which is quite honestly what you will do the most because it's the easiest thanks to the technology nowadays. But we also need to learn substitution and addition, which is where we will actually eliminate variables and then solve for them algebraically. And then whenever we solve things, we're going to be able to identify if they are inconsistent or dependent systems. All that means is when we get an answer or a solution, we're going to be able to say what that means about the system. Where inconsistent is going to mean that there was no solution, and dependent is going to mean that there's infinitely many solutions. So we've actually seen those two descriptions before when talking about equations: inconsistent and dependent equations. Inconsistent was unsolvable, dependent meant it's already solved. And so those are the things we've seen. But let's go ahead and get right into it. So the application here is a real life thing that I've dealt with. And believe it or not, you can use math in real life if you want to. So it says, my parents live in Southern California, and so I make the drive out there, it's about 350 miles, a couple times per year. Disneyland is nearby, and so one time I brought some friends back from Phoenix to see my hometown and go to the theme park. When it was time to come back to Phoenix, we departed in two cars. The car I was driving left at 10 a.m. and drove 80 miles per hour. The other car left at 10:15, so 15 minutes later, and drove a ridiculous 90 miles per hour. Don't do that. Speeding is bad, kids. So the question is, did the other car pass me before making it to Phoenix? And if they did, what time did they pass me at? So now one of these equations I have down below is actually pretty easy to acquire because we've learned how to graph already in this class. So the fact that I left at 10 a.m., drove 80 miles per hour, and the trip was 350 miles, allows me to pretty easily write this 350 minus 80x equation, where 350 is the starting distance, and this negative 80, because I'm driving 80 miles per hour, every 1 hour, which is what x represents as hours, every 1 hour I get 80 miles closer. So 350 minus 80x is going to give me how far away I am after x hours. The one below it is a little bit more complicated. The 350 minus 90 should look almost the exact same, where it's the starting distance of 350 minus 90 because it said 90 miles per hour for the other car. But this part right here might seem a little weird, the x minus 4. And that's to account for the fact that they left at 10:15 instead of 10 a.m. So now you should think to yourself, well, how does a 15-minute difference become x minus 1/4 over here? It's because 15 minutes is 1/4 of an hour. Okay, so 15 minutes equals 1/4 hour. And so this x minus 4 part says for every x hours I've driven, they've driven 1/4 of an hour less. So for example, if I've driven 2 hours, x for me would be 2, but if I plug in 2 hours for them, they've actually driven 2 hours minus 1/4 hour, which would be 1 hour and 45 minutes. So what I'm doing here, this x minus 1/4, is just subtracting that 15-minute difference. Okay, so now all that being said, we will come back and solve this problem graphically after we've gone through the lesson and we've seen all the steps. But writing these equations is always the hardest part to get these word problems done. So I wanted to give you those now. That way, if you want to try this at the end, or try it at any point throughout the lesson, you can go ahead and come back to these equations. Right. Now, systems of linear equations have three possibilities for how they can play out. When we say we have a system of equations in two variables, that means we have two straight lines. But the way we position those two straight lines can give us three different possibilities. So If the lines intersect the way the left picture does, then the solution to that system of linear equations is the point x comma y where they intersect. So this x comma y would be this dot on the graph right here, which you can see is labeled in that picture. If that's the case, we call this being an independent system, where it's independent because one line does not depend on the other. And I like to think independent, if you're an independent person, you do a lot of stuff by yourself. So there's one solution, just like you do a lot of things one-on-one with yourself. Okay, so that's the best case, is where the lines cross and you get one solution where they cross. The graphical method will show us that one solution really easily, where all we have to do is plot the two lines on Desmos and tap the lines, and it'll tell us exactly what that intersection point is. Okay, the next one is called being inconsistent. This is when the lines are parallel. So think of railroad tracks. The two lines just run right alongside each other. They will never intersect, so there is no solution. So we call that being inconsistent, where there is no solution. The lines never intersect each other. And the third option, dependent system, it's the same line twice. So even though it looks like one line, it's actually just the same line right on top of itself. So if the two lines are the exact same line, we get a dependent system where they're always intersecting, and so there's infinitely many solutions. Any point on the line counts as a solution. All right, so now let's see how to solve. So the easiest method is the one we're going to do first, because you should always use the graphical method to check your answers when you do it the other ways. On your test, I will force you to do it a specific way, but you can always come back to the graphing method to check if you got things right, and it might just give you a head start to getting to the answer anyway. So all we're going to do is type both equations into Desmos, click on the dot, and see where they intersect. So real quick, before we use Desmos, I want to show you guys that you can do this by hand. So if I label the top line in blue and the bottom line in red, I can just go ahead and graph these two lines. The first one is negative 2x minus 4. That means it has a y-intercept of negative 4 and a slope of negative 2, which means it's going to go down 2 and to the right 2. So up here, m equals negative 2, which either means negative 2 over 1, down 2, right 2, or it means 2 over negative 1, which means up 2, left 1. So sorry, either down 2, right 1, or up 2, left 1. So because I'm at the bottom of my graph, I'm going to go up 2, left 1, up 2, left 1, up 2, left 1. You just keep doing this until you run out of space. Then I can go ahead and draw a line through all my dots. Okay, so that's all fine and good. Let's go ahead and graph the other one now in red. Negative 1/2 x plus 2. So if I start trying to graph this, y-intercept of 2, and the slope is negative 1/2, that means down 1, right 2. So down 1, right 2, down 1, right 2, down 1, right 2. If I go the other way, it's up 1, left 2, up 1, left 2, up 1, left 2. And notice what happens. These lines are going to intersect, but I can't actually see the intersection because I ran out of space on my graph. What am I supposed to do with that? And so if I were to continue these lines, I would actually be able to see where they intersect. So if I get my scratch work out of the way here, if I continue these two lines, they will intersect at negative 4, 4. So if I keep this one going, and I keep this one going, okay, this spot where they intersect, you can see the y value right there is positive 4, and if we trace this x value down, it's at negative 4. So negative 4, 4 is my solution. X equals negative 4, y equals 4, which is just the point, negative 4, 4. Okay, but notice that graphing becomes annoying really fast. No one really, I mean, to my knowledge, enjoys doing the graphs because nowadays we have Desmos. So what you can do is flip over to Desmos. Looks just like this. And you can see I have the two equations on the left side of the screen typed in. Negative 2x minus 4 is the purple line. Negative 1/2 x plus 2 is the black line. And all I'm going to do is tap on the line. Notice that gray dot appeared. And if I tap the gray dot, it tells me exactly what that intersection point is. So I really don't have to do any work. I just type in the equations, tap the dot, and it tells me negative 4, 4 is the answer. So it's really that easy to use the graphical method on Desmos. You could do all this by hand, but realistically, the graphing calculator is much better at graphing than we are. All right, so now that is what you will fall back on to check your work, and that works all the time. You can always do that for these kind of questions, but we need to know how to do it in other ways because it applies to other concepts in mathematics. So although for this specific case, just finding the solution, this works, we also need to do things algebraically because as you go through your mathematical careers, you're going to have situations where you need these skills of algebra, even though there's an easier way to get to the answer right now. So just keep that in mind. All right, first one is called substitution. Okay, we have been doing this the whole time. I just never called it this. So substitution, notice we have two equations here. Substitution is when you take one equation and plug it into the other. So what I'm going to do is take, the first one says y equals 4x minus 2. This 4x minus 2 is going to go into that second equation for the y. So I can rewrite this second equation as 3 times 4x minus 2 minus 2x equals 4. Where again, that 4x minus 2 is what y equals from the first equation. So because I see a y right here, I can replace y in the second equation with what I know y is equal to. And we've done this in the nickel and dime type questions in the past. We just didn't necessarily call it a system of equations. All right, now solving is pretty easy. We're going to distribute the 3. When we do that, we get 12x minus 6, and we still have a negative 2x and a 4 on the other side. If we combine like terms, 12x minus 2x is 10x, so we have 10x minus 6 equals 4. Add 6 to both sides, and we get 10x equals 10. Divide by 10, and we get x is equal to 1. This is half of the answer, okay? But we need the other half of the answer, so I need to take the other equation, y equals 4x minus 2, and plug in this x equals 1 I just got. So when I do that, I'll get y equals 4 times 1 minus 2. 4 times 1 is just 4. 4 minus 2 is 2. So I get y equals 2. Now my answer is the coordinate x equals 1, y equals 2. So it's the whole thing 1 comma 2. But it's that easy. If you want to do this on Desmos, all you do is type in the two equations the way you see them, click the dot where they intersect, and it'll intersect at 1 comma 2. Because we got one answer, by the way, this is a independent system. Okay, 1 comma 2, and this is an independent system because we got one solution. Okay, number 3, we're going to solve this system using substitution, so we need to use the same approach. We have to substitute, but notice in that first equation, nothing is isolated. So when I look at this equation here, no letter is by itself. The way it was in the other one, we had y equals something. We want that same thing to appear. So what I'm going to do is rewrite this first equation to get y by itself. So if I add 3x to both sides, this becomes y equals 3x minus 9. Okay, all I did was take this 3x right here and add it to the other side. Now I can go ahead and replace y in the second equation with what I know y is equal to. So this second equation is going to become 10x plus 9, and then where I see the y, I'm going to write 3x minus 9, and this is equal to 67. So again, this y right here, 3x minus 9, got replaced in that second equation because I have y equals here, and I have a y over there I can plug it in for. Think of this like an Indiana Jones, where he has to steal the little thing off the podium. Sorry, I'm struggling here. You know, the Indiana Jones where the big ball ends up rolling after him. And so what he does is he shakes a bag of coins in his hands, and he's like, this feels like it's about the right size. And he quickly switches out the item he's stealing for the bag of coins. It's the same idea. We're trying to make an equal exchange here, where we know what y is, so we're trying to switch it out for something that's exactly the same. In this case, 3x minus 9. All right, now we're going to distribute this 9 because now we're just solving for x. So we have 10x, and then 9 times 3x is 27x. 9 times negative 9 is negative 81. Still equal to 67. I can go ahead and combine like terms to get 37x minus 81 equals 67. When I add the 81 over, 37x is going to be equal to 148. And if I divide 138 by 7, ooh, hopefully that comes out to a nice clean number. 37 times 4 is going to do it. So x is going to be equal to 4 there. All right, now that's only half the answer, though. We need to take the first equation, y equals 3x minus 9, and plug our x value back in to find out what y is. So when I do that, I get y equals 3 times 4 minus 9. 3 times 4 is 12. So this gives me y equals 3, which makes my overall answer 4, comma 3. And because we got one answer, this is again an independent system. Okay. Independent system means these lines cross, they make an X when they cross, and they cross at the point 4, comma 3. For the record, by the way, I want to clarify, I'm always plugging this X I get into the first equation right now. So this X I got, I chose the first equation to plug it into. You can actually plug it into either of these two equations, but you want to plug it into the easiest possible spot. So the reason I'm choosing this one that says y equals 3x minus 9 is because it has y by itself, and I'm trying to get y as my answer. So if the equation already has y isolated, it makes it a lot less work to get y equals 3. If I were to plug x into this first or the second equation over here, 10x plus 9y equals 67, I'll still get y equals 3, but it'll be a lot more work. And we want to work smarter, not harder. Okay, so we choose the easiest thing to plug it back into. All right, so that was substitution. Now we're going to solve two problems using addition. Okay, addition is used to add the two equations together to get a variable to cancel out. The first one here, number 4, is going to be a lot easier than the second one because things already line up. So if you're thinking number 4 seems too easy, number 5 will take it up a notch, and we'll do a little explanation there. But okay, so our goal with elimination is to literally eliminate a variable. So when we say addition up here, we really mean eliminate one variable. So we're trying to add the two equations together, use addition to get rid of one of the variables. In this first problem, number 4 here, notice 2x and negative 2x are right on top of each other. Our job is to add these two equations together so that these x's cancel. So watch what happens. If I just put a plus sign here, and I turn this into an equation, 2x minus 2y equals 10 plus that entire bottom equation, negative 2x minus 3y equals 5, I add vertically just like I would normally. So 2x minus 2x gives me a 0 there. Negative 2y plus negative 3y is negative 5y. And 10 plus 5 is 15. So now this just says negative 5y equals 15. And if I divide by negative 5, I get y equals negative 3. Look how quick and easy that was to get what y is. Okay, but there's a couple things we need to talk about going on here. One is why. Why am I allowed to do this? Okay, so the main thing you need to realize here is that there's an equal sign here that says 5 is equal to negative 2x minus 3. The fact that they're equal is the reason I can do this. Because what I'm actually doing is I'm adding 5 to the right side of the equation, and I'm adding negative 2x minus 3y to the left side of the equation. And you're thinking, Mr. K, didn't we learn we have to add the same thing to both sides? So you might be thinking to yourself, if I do plus 5 here, I need to also do plus 5 on the right. That's what we learned in the past. The thing is, I am doing that, okay? By adding 5 on the right side and negative 2x minus 3 on the y on the left side, I'm adding the same thing to both sides because they're equal to each other. So if they weren't equal to each other, if this said not equal, then this wouldn't work. I can't just add things willy-nilly to an equation. But because both sides of this equation are equal, I can add one side to the left and the other side to the right, and the equation stays true because I'm adding equal things to both sides. Okay, so now we have y equals negative 3. We still need the other half of this answer. So now I have to choose an equation to plug y equals negative 3 back into. It does not matter which equation we choose, so just choose the easier one. But in this case, they're basically the same, right? They don't look too different. So I'm just going to arbitrarily choose the top one, which means for no real reason. I'm going to take y equals negative 3 and plug it in up there. So I get 2x minus 2 times negative 3 equals 10. Doing a little work here, I get 2x plus 6 equals 10, which means subtract 6 from both sides, 2x is equal to 4, and so x equals 2. That means my final answer is 2 comma negative 3, where this is again an independent system because we get one answer. Okay, independent just means we have two different lines that intersect each other, and they intersect in this case at 2, negative 3. All right, that was the easy version of these questions. Now number 5 is going to take it up a notch. If we try to do the same approach, so if I just add together the two equations for number 5 right now, these aren't going to cancel anything out. Because negative 3x plus 4x is 1x, and 2y plus negative 3y is negative 1y, the y's and x's don't go away. Okay, we need what happened in number 4 to happen in number 5, where these two x's and negative 2x's canceled to give us a 0 here. So that requires these two numbers here to be opposites of each other, 2 and negative 2. Here I don't have that. I have negative 3 and 4, or I have 2 and negative 3. Those don't line up to cancel out. So what I need to do is choose one variable and multiply both equations by a number that'll make that variable cancel out. So what I always tell students is choose the smaller numbers. So 3 and 4 are bigger than 2 and 3. Not by much, but a little bit. So I'm going to focus on the y variable because the numbers are smaller. Okay, 2 and 3 are pretty small. So now what I need to do is find the least common multiple of 2 and negative 3. Or the negative in this case doesn't matter, so just of 2 and 3. So the LCM of 2 and 3 is equal to 6. So that means I need to rewrite these equations so that way the coefficient of y is going to be 6. Okay, so the way I achieve 6, think about finding common denominators in the past. We would find the least common multiple of the denominators and then multiply both fractions, top and bottom, to get that least common denominator. Here it's the same idea. I need to make the y components both have a coefficient of 6. So I'm going to multiply the top equation by 3 because 3 times 2 will give me 6. Now I'm going to multiply the bottom equation by 2 because, again, 2 times 3 will give me 6. Okay, so now I'm going to rewrite each equation. Okay, the top equation, if I multiply everything up here by 3, because the 3 has to go to everywhere in order for this to be valid. If I multiply everything by 3, I get negative 9x plus 6y equals 12. And for the bottom equation, I distribute the 2 to everywhere inside. I get 8x minus 6y equals negative 26. Okay, now that I have the y coefficients as opposites, now I can add the equations together. So if I add the top and bottom equations together, negative 9x plus 8x is negative 1x, 6y minus 6y is 0, and 12 minus 26 is negative 14. So if I simplify this, this says negative x equals negative 14, which means x is positive 14. All right, not so bad. Now we're halfway done. We need to now get the y component. So what I'm going to do is choose one of the equations and plug that x value back in. So for no real reason, I'm going to choose the top equation. Again, it does not matter. You just got to pick one. So negative 3x plus 2y equals 4. And I'm going to plug in this x equals 14. So negative 3 times 14 plus 2y equals 4. This is negative 42 plus 2y equals 4. If I add 42 to both sides, I get 2y is equal to 46, which means y equals 23. Putting together my two answers, x is 14, y is 23, my overall answer is 14 comma 23. And because we got one answer, this is again an independent system. All right, so that is how you solve systems using addition. The key is to eliminate one variable so you can solve for the other, and then plug that variable back in to get the one you're missing. Okay, now we're going to talk about what happens when systems are inconsistent or dependent. So we're going to get two possibilities here. One will be inconsistent, one will be dependent, just to show you what it looks like. So let's go ahead and start with the left one. Number 6 says solve using any method. So we want to choose the easier method. Usually the easier method is going to be the method that involves getting y isolated when y already does not have a coefficient. So what I mean by that is y is all by itself over here. If I just subtract this 3x to the other side, then I'll have y completely by itself. So I can rewrite this top equation as y equals negative 3x plus 17. Or again, I just took this 3x and subtracted it to the other side. The bottom equation I can now plug y into. So if I take negative 3x plus 17 and put it in for y right there, this bottom equation comes 3 times negative 3x plus 17 is equal to negative 9x plus 51. Or again, all I did was plug in what y is equal to, where I see a y in that second equation. So now I distribute, I get negative 9x plus 51 is equal to negative 9x plus 51, and hey, that's weird. These are the same. So, same. Okay, when you get two things that are the same, that means this is a dependent system. Okay, so this is a true statement always. Negative 9x plus 51 always equals negative 9x plus 51. So when they're the same, this is always true. Okay, always true. So dependent. Okay, this means that there is infinitely many solutions. And the reason there's infinitely many solutions is solutions to systems of linear equations represent the intersection points, but these are the same line, meaning they're always intersecting because they're right on top of each other. Okay, so if you were to write each of these original lines in slope-intercept form, we already wrote the first one, y equals negative 3x plus 17. If I were to divide the second equation, everything by 3, I would also get y equals negative 3x plus 17. So now notice these two equations are the same. It's just the same line twice. Okay, so that is a dependent system which has infinitely many solutions. No matter what you plug in for x, you'll get an answer for y. Okay, number 7 is going to be the opposite. We're going to get no solutions. Let's see why. We already have y isolated in this second equation. So let's go ahead and plug that in for y in the first equation. So that top equation will become 5x plus 12, because I'm plugging that in for y, minus 5x equals 9. Or again, I took 5x plus 12 and I plugged it in for that letter y. This simplifies on the left to just be 12, because 5x and negative 5x cancel each other out. So I have 12 equals 9. This is false. Okay, because this is false, this is an inconsistent system, which means no solution. And we can denote that with a circle with a line through it. Okay, the reason there's no solution is these lines will never intersect. If we rewrite the top equation by adding 5x to both sides, it looks like y equals 5x plus 9. So now notice that we have 5x plus 9 and 5x plus 12. These two lines have the same slope, 5 and 5, but they have different y-intercepts, 9 and 12. So when you have the same slope but different y-intercepts, that means you're parallel lines which will never intersect. So we end up with no solution. Okay, now on to the applications. Number 8 we've seen a bunch of, so we should actually be good at number 8. Number 9 is going to feel new. So what we're going to do is we're going to set these up, and then we're going to solve them graphically. Okay. So number 8, it says a man has 13 coins in his pocket, all of which are dimes and quarters. If the total value of his change is 205 cents, how many dimes and how many quarters does he have? Okay, so he has 13 coins. If you have 13 coins in your pocket and they're dimes and quarters, if we let D represent number of dimes, so D is going to equal number of dimes, and Q represent number of quarters, then if we add these two values together, D plus Q, this needs to equal 13, which is the total number of coins we have. Okay, but then the second equation says the total value of his change is 205 cents. So if we add up all of the money in dimes and the money in quarters we have, it needs to equal 205. So 205 is going to equal, a dime is worth 10 cents. So 10 times D represents 10 cents times every dime, plus a quarter is 25 cents. So 25Q, 25 cents times every quarter. Together, these two equations are going to give us our solution. So dimes plus quarters equals 13, because there's 13 coins. 205 equals 10D plus 25Q, because there's 10 cents for every dime and 25 cents for every quarter. If you add that all up, you get 205 cents. So now we could solve the first equation for D or Q and substitute that into the second equation. But I want to show you guys that once you get the hang of this, you're going to end up using Desmos in real life for most of these problems anyway. So I'm going to show you how to do this on Desmos real quick. I mean, we already saw how, but we're going to make it solidified now. So our first equation, I'm going to turn these other two off here. I'm going to type in, instead of D plus Q, I'm going to say X plus Y equals 13. And I'm using X and Y on Desmos because graphing, it prefers X and Y. So X is D and Y is Q in this case. Okay, my second equation was 205 equals 10. And instead of D, I'll put X, plus 25. Instead of Q, I'll put Y. Notice up here on the graph, these lines intersect at the point 8, 5, where that 8 represents my X value, which is actually the D value. Okay, so over here on the left, I'm going to write, using Desmos, we get the point 8, 5, which is going to represent 8 dimes and 5 quarters. Okay, so the X value of that point represents dimes, the Y value of that point represents quarters, because the way I typed it in, I used X for dimes and Y for quarters. All right, so 8, 5, and it's that easy. Now we can just double check that this works. 8 dimes is 80 cents. 5 quarters is $1.25. 80 cents plus $1.25 is 205 cents. So we're all good there. We can go ahead and put our calculator away. Now number 9. It says Jolene invests her savings in 2 bank accounts, one paying 5% and the other paying 12% simple interest per year. She puts twice as much money in the lower yielding account because it is less risky. Her annual interest is $7,040. How much did she invest at each rate? Okay, so the easier equation right here is she puts twice as much in the lower yielding account. Okay, so if we let X represent amount in 5% account, so is the amount of money she puts in the first account, and Y represent the amount in the 12% account, then the fact that she puts twice as much in the lower yielding account means X is going to be equal to 2Y. Because however much money she puts in the high savings account, the 12% account is our Y, however much is here, you multiply that by 2, and that's how much is in the lower yielding account. So she puts twice as much in the lower yielding account, X is equal to 2Y. Now the second one says she's getting simple interest on the amount she invested that adds up to $7,040. So simple interest is calculated by multiplying the amount invested times the percentage. So if you want to calculate how much interest you get at 5%, you multiply 0.05, which is 5% as a decimal. Remember, early on in this class, we learned how to turn percents into decimals. So 0.05 multiplied by X, this is the amount of interest she earns from the 5% account. And we add this to 12% is 0.12 multiplied by Y. That's the amount of interest she earns from the 12% account. And this is supposed to be equal to 7,040. So the amount of interest from the lower account plus the amount of interest from the higher account gives you the total amount of interest earned. So now we're just going to take this over to Desmos, graph both these things again. So our two equations are X equals 2Y and 0.05x plus 0.12y equals 7,040. Okay, in this case, I need to zoom out a bit to see where these actually intersect. So let's see, keep going, keep going, keep going, keep going. Oh, way over there. If I tap that dot where they intersect, it says 64,000, 32,000. Notice the 64 is double the 32. 64 represents the amount of x, which is the amount in the lower yielding account, and 32 represents the amount in y, the higher yielding account. So over here on my notes, I'm just going to say used Desmos, and we get the point 64,000, 32,000. Probably shouldn't use commas there. Okay, 64,000, 32,000. And if we say what this actually represents, this means that Jolene, great name by the way, Jolene invests $64,000 at 5% and $32,000 at 12%. All right, we got one more question. We got to finish off that title slide now. So up here, we have our two equations already from before. Remember, this is two cars driving from the LA area to the Phoenix area, so 350 miles. One going 80 miles per hour, the other going 90, but one car has a 15-minute head start. Now, the reason this question exists here is because I was driving with someone, and they asked me, hey, do you think they'll catch us? And I said, well, how fast are they going? And they said 90. I knew I was going 80. So as I'm driving, I actually calculated when they would pass us based on those numbers. And we looked out the window at that time, and sure enough, there they were, driving right by us. So they do, in fact, catch us. Let's see how quickly, though. So if I pull Desmos back out, I have these equations already typed in. If I turn on the graphs, okay, notice the lines look like they're almost on top of each other. That's because the slopes are very similar. You can change the axes on Desmos to show you what you need. So I'm going to change the x-axis to go from 0 to, in this case, just 5, and the y-axis to go from 0 all the way up to 370. That way we can fit all the mileage in. So now you can see these two lines are going to intersect at that point shown, 2.25, 170. So again, I'll write using Desmos. We intersect at 2.25, 170. So now let's say what this actually represents. Okay, the y value here in our equations, y equals 350 minus 80x in this first equation. This is the starting distance minus how much we've driven. So this y value represents how many miles are left. Okay, so it says over here, not when did they pass us in terms of distance. Okay, it just says, did the other car pass us before making it to Phoenix? So yes, they passed us with 170 miles to go. Then the actual question here is what time? So this 2.25 for x right here represents how many miles it's been. Okay, so if we take our answer here and we break it down, this says that they passed us with 170 miles to go after 2.25 hours of driving. So now the question is, if we left at 10 a.m., what time is it 2.25 hours after driving? Well, 2.25 is 2 hours, 15 minutes, because 0.25 is a quarter hour, it's 15 minutes. So 2 hours, 15 minutes after 10 a.m., this is at 12:15 p.m. they passed us. Okay, because I'm adding the 2 hours, 15 minutes to the 10 a.m. time that we left. So they passed us at 12:15 p.m. right after lunch. And believe it or not, I looked out my window at 12:15 and there was my friend Mitchell and company driving by. And that's how you can use math in real life. Thanks for joining me. See you guys next time.